4.5 billion years from now, our galaxy will collide with Andromeda. And at the heart of that distant spiral lies something extraordinary, a supermassive black hole containing the mass of 100 million suns. Tonight, we'll explore this cosmic encounter step by step, using real astronomical data, gravitational physics, and the gentle mathematics of orbital motion that govern our galactic destiny. It's a story of space-time curved beyond imagination, stellar streams pulled into new configurations, and two ancient black holes performing a slow, inevitable dance toward merger. The timeline stretches far beyond human experience, yet the physics unfolds with quiet precision we can understand today. If this tearful journey through deep time helps you relax or discover something new about our cosmic future, your gentle like, your soft subscribe, and your thoughtful comments mean more than you know. There's no urgency here, just the patient unfolding of gravitational forces that have been drawing these galaxies together for billions of years. Now let's begin this slow exploration of M31's supermassive heart and what it means for our distant future. What if I told you that your future has already been written in the stars, not in years or decades, but in billions of years stretching ahead like an infinite ocean of time? Hello there, and welcome to Science for Sleep, where tonight we begin a gentle journey toward understanding one of the most extraordinary cosmic events awaiting our galaxy. Perhaps you're settling into bed right now, or maybe you're curled up somewhere comfortable as evening draws near. And if this peaceful exploration helps you discover something fascinating about our universe's distant future, your gentle like, your quiet subscription, and your thoughtful presence here mean more than you might imagine. Tonight we're going to explore something that sounds almost like science fiction, but represents hard scientific reality. In approximately 4.5 billion years from now, our Milky Way galaxy will collide with the massive Andromeda galaxy. And at the heart of that approaching spiral lies a supermassive black hole containing the mass of over 100 million suns. These timescales might seem impossible to grasp at first, so let's think about them this way. If the entire history of Earth were compressed into a single year, human civilization would occupy only the last few seconds before midnight on December the 31st, while the collision we're discussing tonight that it would happen sometime during the next full year. There's something profoundly comforting about these vast temporal scales, isn't there? Because they remind us that the universe operates with infinite patience, unfolding its grand transformations across periods so long that mountains rise and fall like waves, continents drift like clouds, and even the positions of stars shift dramatically across the sky. The event we're exploring tonight won't affect anyone alive today, or their children, or their children's children for thousands upon thousands of generations. Yet understanding this cosmic destiny helps us appreciate both our place in the universe and the magnificent processes that shape reality itself. Scientists have been studying this approaching encounter for decades now, using powerful telescopes, sophisticated computer simulations, and careful measurements of how galaxies move through space, and what they've discovered is a story of gravitational choreography playing out on the largest possible stage. The Andromeda galaxy, also known as M31, currently sits about 2.5 million light-years away from us, which means the light reaching your eyes from that distant spiral began its journey toward Earth when our earliest human ancestors were just learning to walk upright across African plains. But here's what makes this story so remarkable. Andromeda isn't simply sitting still in space like a distant lighthouse. Instead, it's moving toward us at approximately 250,000 miles per hour, drawn by the inexorable pull of gravity across the cosmic void. This might sound alarming initially, but remember that even at such tremendous speeds, crossing the gulf between galaxies takes billions of years, giving time for countless stellar generations to be born, live their entire lives, and fade away before anything dramatic occurs. When we look up at the night sky and see the faint smudge of the Andromeda galaxy with our naked eyes, we're actually witnessing our cosmic future approaching, slowly and majestically, like a vast ship sailing across an ocean of space-time. The remarkable thing about studying such distant future events is that we can predict them with reasonable confidence because gravity operates according to well-understood physical laws. And while there are certainly uncertainties about exact timing and specific details, the basic outcome seems inevitable given our current understanding of galactic dynamics. So as we embark on tonight's exploration together, there's no need to worry about memorizing complex equations or struggling with intimidating technical details. because our goal is simply to develop an intuitive appreciation for one of the most spectacular cosmic events in our galaxy's future, allowing these ideas to settle gently into your mind like snowflakes landing on still water. Whether you're listening from a cozy bedroom, a quiet living room, or perhaps even outside under the actual stars we're discussing, you're part of this cosmic story unfolding across deep time. And understanding our connection to these vast processes can bring a sense of wonder and perspective that enriches how we see ourselves and our place in this magnificent universe. What would you see if you could somehow step outside our galaxy and observe the cosmic neighborhood surrounding us like a vast celestial city? The Andromeda galaxy, designated M31 by astronomers, stands as our nearest major galactic companion, a magnificent spiral containing over 1 trillion stars that dwarfs even our own impressive Milky Way with its 300 billion stellar inhabitants. To understand the immense distance separating us from this approaching giant, imagine light itself as the fastest messenger in the universe, capable of circling Earth's equator 7 times in a single second. Yet when photons depart from Andromeda's glowing spiral arms, they must journey through the vacuum of space for 2.5 million years before reaching your retina tonight. This means that looking at Andromeda provides a glimpse into deep cosmic history, showing us how that galaxy appeared when our planet was experiencing ice ages and early human ancestors were developing primitive tools across African landscapes. The scale of this distance becomes even more remarkable when we consider familiar earthly measurements. If you could somehow drive a car toward Andromeda at highway speeds, maintaining 60 miles per hour continuously without stopping for fuel or rest, the journey would require approximately 28 billion years to complete, which is twice the current age of the entire universe. Yet despite this seemingly insurmountable gulf, Andromeda approaches our galaxy with relentless gravitational determination, racing through intergalactic space at roughly 250,000 miles per hour, fast enough to travel from New York to Los Angeles in less than 60 seconds. This velocity might seem extraordinary by earthly standards, but in the context of cosmic distances, Andromeda's approach resembles a massive ship slowly crossing a vast ocean, taking billions of years to traverse the space between galaxies. The approaching galaxy presents itself as a true cosmic giant, stretching approximately 220,000 light-years from edge to edge, making it roughly twice the diameter of our own galactic home. Within this enormous spiral structure, countless stellar nurseries birth new generations of stars while ancient red giants exhale their outer layers into space, creating the complex ecosystem of gas, dust, and starlight that defines galactic evolution. From our earthly perspective, Andromeda appears as the most distant object visible to unaided human vision, manifesting as a faint, elongated smudge in the constellation bearing its name during autumn evenings in the northern hemisphere. Ancient Persian astronomer Abd al-Rahman al-Sufi first recorded this nebulous cloud in 964 CE, describing it as a small, misty patch that seemed different from surrounding stars. For centuries, observers puzzled over this mysterious object until technological advances finally revealed its true nature as an entire galaxy comparable to our own, containing billions upon billions of individual suns arranged in graceful spiral patterns. When you step outside on a clear, moonless night away from city lights, you can actually glimpse this cosmic leviathan with your naked eyes, seeing photons that began their journey when our species was still learning to control fire and develop language. The visual experience connects you directly to cosmic scales that dwarf human imagination, yet somehow our minds can grasp these concepts and find meaning in such vastness. What makes Andromeda particularly fascinating extends beyond mere size and proximity. This galaxy exhibits complex internal structure with multiple spiral arms, star-forming regions, and a dense central bulge packed with ancient stellar populations. Recent observations reveal that Andromeda has experienced previous galactic encounters throughout its history, absorbing smaller companion galaxies and growing larger through cosmic cannibalism over billions of years. The galaxy's outer regions show evidence of these past mergers in the form of stellar streams and disrupted structures that tell stories of ancient gravitational battles. As we contemplate this approaching giant, we begin to sense that something profound awaits discovery at Andromeda's very heart, something that will play a crucial role in determining the ultimate fate of both galaxies when they finally meet in the distant future. The central bulge of this massive spiral harbours secrets that astronomers have only recently begun to understand, containing an object so massive and influential that it shapes the behaviour of trillions of stars across vast distances, orchestrating the cosmic dance that will eventually bring these two galactic titans together in one of the most spectacular events our universe has to offer. What lurks in the absolute darkness at the centre of Andromeda, invisible yet more massive than anything your imagination could conjure? Deep within the galactic core of M31, hidden behind countless layers of stars, gas clouds and cosmic dust, dwells a supermassive black hole containing between 100 and 140 million times the mass of our Sun, a gravitational monster so immense that its influence extends across thousands of light years, orchestrating the motion of entire stellar populations with invisible authority. This cosmic leviathan represents one member of an exclusive class of objects that astronomers have discovered residing at the hearts of virtually every major galaxy throughout the observable universe, serving as the central engines that help regulate galactic evolution over billions of years. To appreciate the sheer magnitude of this hidden giant, consider that our own galactic centre houses a supermassive black hole called Sagittarius A, which contains approximately 4 million solar masses and already defies comfortable human comprehension. Yet Andromeda's central monster outweighs our local heavyweight by a factor of 25 to 35, making it one of the most massive black holes in our cosmic neighbourhood. The comparison becomes even more staggering when we realise that if Sagittarius A were somehow placed at the centre of our solar system, its event horizon would extend roughly halfway to Mercury's orbit, while Andromeda's behemoth would easily encompass the entire orbit of Venus and possibly approach Earth's orbital distance. Despite containing such incredible mass concentrated into a region smaller than our solar system, this gravitational titan currently exists in a state of remarkable quietude, earning it the designation of a dormant or quiescent supermassive black hole that produces minimal electromagnetic radiation across the spectrum. The peaceful nature of M31's central monster contrasts dramatically with its more active cousins found in distant galaxies, where similar objects gorge themselves on surrounding matter and blaze forth as quasars visible across billions of light years. Instead, Andromeda's giant subsists on a meagre diet of occasionally wandering gas clouds and the rare unlucky star that ventures too close to its gravitational domain, maintaining what astronomers describe as an extremely low accretion rate that keeps it nearly invisible to our most sensitive instruments. Recent observations using the Chandra X-ray Observatory have detected occasional flickers of activity from this slumbering beast, including notable outbursts in 2006 and 2013 that briefly increased its X-ray emissions before settling back into relative silence. These sporadic awakenings provide tantalizing glimpses into the hidden processes occurring near the event horizon, where matter occasionally spirals inward and heats to millions of degrees before disappearing forever beyond the point of no return. The discovery and characterization of this massive object required decades of painstaking astronomical detective work, as scientists measured the velocities of stars orbiting the galactic center, noting how quickly they moved in tight orbits that could only be explained by the presence of an extremely compact, invisible mass concentration. The precision required for these measurements pushes the limits of current technology, yet the evidence remains compelling and consistent across multiple independent observations using different techniques and instruments. Understanding the nature of this cosmic giant becomes crucial as we contemplate the future collision between Andromeda and our own galaxy, because the encounter will inevitably bring together two supermassive black holes in a gravitational drama unprecedented in cosmic history. When these galactic titans finally merge in approximately 4.5 billion years, their central black holes will begin an intricate orbital dance that gradually tightens over millions of additional years as they lose energy through gravitational wave radiation. The ultimate fusion of these two massive objects will create a single supermassive black hole containing over 150 million solar masses, accompanied by a burst of gravitational waves so powerful that it will send ripples through the fabric of space-time itself, potentially detectable by advanced civilizations throughout the observable universe. This future encounter represents more than just an abstract astronomical prediction. It embodies the culmination of cosmic processes that have been shaping our local universe since galaxies first began forming in the aftermath of the Big Bang. The gravitational choreography required to bring these two giants together operates on timescales that dwarf human experience, yet follows physical laws that we can understand and predict with remarkable accuracy using the mathematical framework of general relativity developed by Albert Einstein over a century ago. How can something be simultaneously the densest and least dense object in the universe, containing the mass of millions of stars while possessing a lower average density than the water in your evening glass? To understand the extraordinary nature of supermassive black holes like the one residing at Andromeda's heart, we must begin with familiar earthly experiences and gradually expand our perspective across scales that challenge human intuition. Consider starting with something as simple as a marble, which contains roughly the same amount of matter, whether you hold it in your palm or imagine compressing it down to the size of a grain of sand, though the compressed version would become incredibly dense and difficult to handle. Now imagine taking our entire Sun, with its mass of 2 trillion kilograms, and somehow squeezing all that stellar material down to a sphere just 6 kilometers across, creating a stellar mass black hole whose density defies description in ordinary terms. But supermassive black holes operate according to entirely different principles, defined by astronomers as gravitational monsters containing at least 100,000 times our Sun's mass, though the largest specimens can reach billions of solar masses while still maintaining their fundamental character as regions where spacetime curvature becomes so extreme that nothing, not even light itself, can escape once it crosses the event horizon boundary. The supermassive black hole lurking at M31's center weighs in at approximately 100 to 140 million solar masses, placing it firmly in the heavyweight category of cosmic gravitational engines that anchor major galaxies throughout the observable universe. Here's where the physics becomes delightfully counterintuitive. Despite containing such stupendous quantities of matter, this gravitational giant actually possesses an average density significantly lower than liquid water, and in fact approaches the density of air at sea level when you calculate the total mass divided by the volume enclosed within its event horizon. This apparent paradox arises because the event horizon radius grows proportionally with mass, meaning that larger black holes become less dense overall, even as their gravitational influence becomes more powerful and far-reaching across galactic distances. The event horizon of Andromeda's central monster extends approximately 400 million kilometers from the singularity at its heart, creating a spherical boundary large enough to comfortably contain Mercury's entire orbital path around our Sun with room to spare. To visualize this scale, imagine standing at the center of Mercury's orbit and looking outward toward the planet's furthest approach. The event horizon would stretch beyond that distance in every direction, encompassing a volume of space so vast that light itself would require over 22 minutes to travel from one side to the other. Yet this enormous boundary represents merely the point of no return, beyond which the curvature of spacetime becomes so severe that all possible paths lead inexorably inward toward the central singularity where our current understanding of physics breaks down completely. The gravitational influence of this cosmic behemoth extends far beyond its event horizon, reaching outward across dozens of light years to control the motion of stars, gas clouds, and other celestial objects throughout the galactic core region. Stars orbiting within a few light years of the black hole reach velocities approaching 10,000 kilometers per second, moving so rapidly that they complete full orbits in mere decades rather than the millions of years required for stars in our solar neighborhood to circle the galactic center. These extreme orbital speeds provide the primary evidence astronomers use to infer the presence and measure the mass of supermassive black holes, since only such concentrated gravitational sources could accelerate ordinary stars to such tremendous velocities without tearing them apart through tidal forces. The sphere of influence surrounding M31's central black hole encompasses a region roughly 50 light-years in diameter, within which the monster's gravity dominates over all other forces and determines the fate of any matter that ventures too close to its domain. Understanding these scales helps us appreciate why the eventual merger between Andromeda's supermassive black hole and our own galactic center will represent such an extraordinary cosmic event, bringing together two of the most massive objects in our local universe in a gravitational encounter that will reshape the very fabric of space-time across interstellar distances. The physics governing these extreme objects pushes the boundaries of human knowledge, yet follows mathematical principles elegant enough that we can predict their behavior and contemplate their future interactions with confidence grounded in decades of careful observation and theoretical development. Why does the most massive gravitational monster in our cosmic neighbourhood behave like a sleeping giant, barely whispering when it could roar with the power of 1 billion suns? Andromeda's central supermassive black hole currently exists in what astronomers call a quiescent state, operating at energy levels so low that it produces less than 1/10,000,000th of its theoretical maximum luminosity, making it one of the quietest cosmic engines ever discovered, despite containing enough mass to outweigh our entire solar system by factors that stretch human comprehension. This dormant behaviour contrasts sharply with stellar mass black holes found throughout our galaxy, which typically range from 10 to 100 times our Sun's mass and often blaze forth with X-ray emissions as they devour material from companion stars in violent feeding frenzies that can be detected across thousands of light years. The difference lies not just in scale, but in feeding mechanisms, as stellar mass black holes frequently exist in binary systems where they can strip matter from nearby stellar companions, creating superheated accretion disks that glow brilliantly across the electromagnetic spectrum, while supermassive black holes like M31's giant must rely on much more sporadic sources of sustenance in this sparse environment of galactic cores. For over 2 decades, NASA's Chandra X-ray Observatory has maintained a patient vigil over Andromeda's centre, accumulating nearly 900 kiloseconds of observation time across approximately 100 separate pointings that have revealed the subtle rhythms of this cosmic hibernation. These extended observations have documented a baseline X-ray luminosity hovering around 10 to the 36th power ergs per second, which sounds impressive until you realise this represents less energy output than a typical lightning bolt, spread across the entire electromagnetic spectrum of a gravitational monster containing 100 million solar masses. The monotony of this cosmic slumber was dramatically interrupted on January 6, 2006, when Chandra detected an extraordinary outburst that increased M31's X-ray emissions by more than 100-fold, reaching peak luminosities of approximately 4.3 times 10 to the 37th power ergs per second before gradually subsiding over subsequent months. This awakening lasted only briefly in cosmic terms, but provided astronomers with their first glimpse into the violent processes that can occur when significant amounts of material venture too close to the event horizon and spiral inward through the accretion process. 7 years later, in 2013, observers detected another notable flare that, while less dramatic than the 2006 event, still represented a significant deviation from the black hole's typical dormant behaviour, and suggested that these outbursts might occur with some regularity over extended timescales. Stephen Dye Kirby, a research associate at Michigan State University working with the IceCube Neutrino Observatory team, has spent years analysing this accumulated Chandra data to understand the connection between M31's X-ray variability and broader patterns of supermassive black hole activity throughout the universe. His research has revealed that following the major 2006 outburst, Andromeda's central black hole entered what appears to be a more active phase characterized by frequent smaller flares and an elevated baseline luminosity approximately 10 times higher than pre-2006 levels, though still remarkably subdued compared to actively feeding supermassive black holes found in distant galaxies. De Kirby describes this behavior as the black hole winking at us, producing brief flickers of activity that hint at ongoing processes near the event horizon, while maintaining overall quiescence that keeps it nearly invisible to most astronomical surveys. These observations provide crucial insights into the feeding patterns of dormant supermassive black holes, suggesting that they subsist primarily on occasional encounters with wandering gas clouds, disrupted stars, or small amounts of material shed by the aging stellar population surrounding the galactic centre. The sporadic nature of these feeding events explains why M31's monster experiences such dramatic variations in activity on Scylla, sometimes remaining virtually dormant for years before suddenly blazing forth when fresh material becomes available for accretion. The magnetic field structure around the black hole likely plays a crucial role in these outbursts, as tangled magnetic field lines can store enormous amounts of energy before suddenly reconnecting and releasing that energy in brief violent episodes similar to solar flares, but operating on scales that dwarf anything occurring in our solar system. Understanding these feeding mechanisms becomes essential as we contemplate the future merger with our own galaxy, because the collision process will eventually funnel vast quantities of gas and dust toward both galactic centres, potentially triggering sustained periods of intense activity that could transform these dormant giants into blazing quasars visible across cosmic distances before they finally merge into a single, even more massive gravitational engine that will define the heart of our combined galactic future. What cosmic processes could create gravitational monsters so massive that they contain the equivalent of hundreds of millions of stars, and how did these titans grow from humble beginnings to become the architects of galactic destiny? The formation of supermassive black holes like the one lurking at Andromeda's heart represents one of astronomy's most fascinating puzzles, involving multiple pathways that likely operated simultaneously during the early epochs of cosmic history, when the universe was much denser, hotter, and more chaotic than the relatively serene environment we observe today. The most widely accepted scenario begins with the collapse of primordial gas clouds in the first few 100 million years after the Big Bang, when hydrogen and helium created during cosmic nucleosynthesis had not yet been enriched with heavier elements forged in stellar cores, allowing these pristine clouds to achieve masses thousands of times larger than typical, star-forming regions before fragmenting under their own gravity. Some of these massive gas concentrations may have collapsed directly into intermediate mass black holes containing thousands or tens of thousands of solar masses, providing the initial seeds that would eventually grow into the supermassive monsters we observe today through billions of years of subsequent accretion and merging events. Alternative formation mechanisms include the collapse of the first generation of supermassive stars, hypothetical objects that could have achieved masses exceeding 1 million times our Sun before exhausting their nuclear fuel and collapsing into black holes, though the existence of such extreme stellar objects remains highly speculative and dependent on poorly understood conditions in the early universe. Once these initial seeds formed through whatever mechanism, their subsequent growth occurred primarily through the steady accretion of surrounding gas and dust, a process that continues today but operated much more efficiently during the universe's youth, when galaxies contained vastly more available fuel for feeding central black holes. The accretion process involves complex interactions between gravity, magnetic fields, and radiation pressure that determine how rapidly material can spiral inward past the event horizon, with theoretical limits suggesting that black holes can roughly double their mass every 40 to 50 million years under optimal feeding conditions. Andromeda's supermassive black hole has undoubtedly experienced multiple episodes of rapid growth punctuated by quieter periods, with its current dormant state representing just the latest phase in a multi-billion-year evolutionary story that has seen it consume countless gas clouds, disrupted stars, and possibly smaller black holes through galactic cannibalism. Archaeological evidence for this tumultuous history appears in the stellar streams and disrupted structures visible throughout Andromeda's outer regions, which record the gravitational signatures of past galactic mergers that brought fresh supplies of both matter and orbital energy to fuel the central monster's continued expansion. The relationship between supermassive black hole growth and galactic evolution operates as a cosmic feedback loop, where the black hole's gravitational influence helps regulate star formation throughout the host galaxy, while simultaneously depending on that same stellar population to provide the raw materials needed for continued accretion. This symbiotic relationship explains why astronomers consistently observe tight correlations between black hole masses and the properties of their host galaxy bulges, suggesting that these systems co-evolved over cosmic time through processes that remain active today, albeit at much reduced rates compared to the universe's more violent youth. Direct evidence for the presence and mass of Andromeda's central black hole comes from careful measurements of stellar orbital velocities in the galactic core, where astronomers use sophisticated techniques to track the motion of individual stars as they orbit the invisible gravitational source with periods ranging from decades to centuries. These observations reveal stars moving at velocities exceeding 10,000 kilometers per second in tight elliptical orbits that can only be explained by the presence of an extremely compact, massive object containing over 100 million solar masses concentrated within a region smaller than our solar system. The precision required for these measurements pushes current technology to its limits, involving adaptive optic systems that compensate for atmospheric turbulence and spectroscopic techniques sensitive enough to detect Doppler shifts caused by stellar motion across vast cosmic distances. Understanding how supermassive black holes form and grow becomes crucial as we anticipate the future merger between Andromeda and our own galaxy, because this collision will mark the next chapter in both monsters' evolutionary stories, bringing together two massive gravitational engines that have spent billions of years shaping their respective galactic environments in preparation for an encounter that will test our understanding of the most extreme gravitational phenomena the universe has to offer. What invisible forces orchestrate the grandest ballet in our cosmic neighborhood, choreographing the slow-motion dance between trillion-star galaxies across billions of years? The gravitational attraction between our Milky Way and the approaching Andromeda galaxy represents one of the most spectacular examples of celestial mechanics operating on scales that dwarf human imagination, involving forces so subtle yet persistent that they can gradually alter the trajectories of entire galactic systems over cosmic timescales that span most of the universe's history. These two massive spiral galaxies, along with the smaller Triangulum galaxy and dozens of dwarf companions, comprise what astronomers call the local group, a gravitationally bound collection of galaxies that has been slowly contracting under its own collective gravity since shortly after the Big Bang, isolated from the general expansion of the universe by the mutual attraction of its member galaxies. The physics governing this cosmic choreography follows the same fundamental principles that control planetary orbits around stars, though operating on scales millions of times larger and involving masses so enormous that their gravitational influence extends across millions of light-years of seemingly empty space. Understanding the precise details of this galactic encounter requires sophisticated computer simulations that model the motion of millions of individual particles representing stars, dark matter, and gas clouds as they respond to the combined gravitational fields of both galaxies over billions of years of evolution. These N-body simulations push the limits of current supercomputing technology, requiring months of processing time on the world's most powerful machines to accurately track the complex gravitational interactions that determine the ultimate fate of our cosmic neighborhood. Current uncertainties in Andromeda's precise trajectory stem from the extraordinary difficulty of measuring proper motion across such vast distances, where even the most sensitive instruments struggle to detect the tiny angular displacements that reveal how the galaxy moves through space relative to background objects. The Hubble Space Telescope has provided the most accurate measurements to date, tracking the positions of stars within Andromeda across multiple years to determine that the galaxy approaches us nearly head-on with only minimal sideways motion, virtually guaranteeing a direct collision rather than a glancing encounter that might allow one or both galaxies to escape. However, small uncertainties in these measurements translate into significant variations in predicted collision timing, with different studies suggesting first approach times ranging from 3 to 5 billion years depending on assumptions about dark matter distribution, intergalactic medium density, and other poorly constrained parameters. The most recent comprehensive simulations suggest that first close approach will occur in approximately 4.3 billion years, when the outer edges of both galactic halos begin to interpenetrate and gravitational tidal forces start disrupting the orderly structure of spiral arms that currently define both systems. This initial encounter represents only the beginning of a much longer merger process, as the two galaxies will likely experience multiple close passages over several billion additional years before finally settling into a stable combined configuration. The distinction between first approach and final merger becomes crucial for understanding the full scope of this cosmic transformation, because the most dramatic phases of galactic restructuring occur during the later stages, when both systems have lost enough orbital energy through gravitational wave emission and dynamical friction to remain permanently bound together. Computer models indicate that the complete merger process could require up to 10 billion years from initial contact to final equilibrium, making this one of the longest duration events in cosmic history, while simultaneously representing just a brief episode in the ongoing evolution of galactic structures throughout the universe. The orbital mechanics governing this encounter involve concepts familiar from planetary astronomy, but scaled up to galactic proportions, where conservation of energy and angular momentum determine the shapes and orientations of the merger remnants, just as they control the behavior of comets orbiting our Sun. Dark matter plays a particularly important role in these dynamics, as the invisible halos surrounding both galaxies contain several times more mass than all their visible stars combined, creating gravitational potential wells that extend far beyond the luminous boundaries visible in telescope images. The timing of galactic collision also depends on the resistance provided by the intergalactic medium, a tenuous plasma of hydrogen and helium gas that permeates the space between galaxies and creates drag forces that gradually slow orbital motion over cosmic timescales. Understanding these complex interactions helps astronomers predict not only when the collision will occur, but also what the combined system will look like after billions of years of gravitational reshaping, setting the stage for comprehending how the supermassive black holes at each galactic center will eventually find each other in the chaos of merger dynamics and begin their own spectacular dance toward ultimate fusion. What happens when two cities containing hundreds of billions of inhabitants crash into each other, yet despite the apparent chaos, virtually none of the residents actually collide with one another? The reality of galactic mergers defies our everyday intuition about collisions, because the word itself conjures images of catastrophic destruction and violent impacts that simply don't apply when dealing with the vast scales and sparse densities that characterize galaxies like our Milky Way and approaching Andromeda. The average distance between neighbouring stars within a typical galaxy exceeds 100 billion miles, creating a cosmic environment so empty that if our sun were represented by a marble sitting on your kitchen table, the nearest stellar neighbour would be another marble located roughly 400 miles away. This extraordinary emptiness means that even when two entire galaxies interpenetrate each other during a merger event, the probability of any individual star physically colliding with another approaches essentially zero, making galactic collisions remarkably gentle affairs despite their awesome scale and duration. Instead of destructive impacts, astronomers observe what might be better described as a cosmic pinball effect, where stars get gravitationally scattered into new orbits without ever coming close enough to touch, bouncing off invisible gravitational fields like balls on a three-dimensional billiard table that stretches across hundreds of thousands of light years. The gravitational forces responsible for this stellar reshuffling operate through complex tidal interactions that gradually redistribute orbital energy throughout both galactic systems, causing some stars to be flung outward into elongated elliptical orbits, while others spiral inward toward the emerging centre of the combined system. These tidal effects become particularly pronounced when galaxies of comparable mass encounter each other, as neither system dominates gravitationally, leading to symmetric distortions that create spectacular tidal tails and bridges visible in deep telescope images of ongoing galactic mergers throughout the universe. The formation of what astronomers playfully call Milkomeda will unfold over approximately 10 billion years, during which both spiral galaxies will gradually lose their distinctive arm structures and settle into a more spherical configuration, resembling the giant elliptical galaxies commonly observed in galaxy clusters. This transformation occurs because spiral arms represent relatively fragile density waves that cannot survive the gravitational chaos of a major merger, leaving behind a more dynamically relaxed system where stars move in random elliptical orbits rather than the organized circular patterns that maintain spiral structure. The process resembles watching two hurricanes merge in slow motion, where the organized rotation patterns of both storm systems eventually dissipate into a larger, less structured weather formation that retains the total mass and energy of both original systems while exhibiting completely different dynamical properties. During the merger process, vast streams of stars will be ejected from both galaxies, creating extended tidal features that can stretch across millions of light years and remain visible for billions of years as archaeological evidence of the encounter. Some of these stellar streams will eventually fall back into the central merged system, while others may escape entirely, forming a sparse halo of orphaned stars wandering through intergalactic space with no host galaxy. The gravitational interactions responsible for these dramatic restructurings follow the same physical principles that govern planetary motion, scaled up to involve trillions of individual objects moving under the combined influence of dark matter, halos containing several times more mass than all visible stars. Computer simulations reveal that the merger timeline depends critically on the initial approach velocity and angle, with head-on collisions producing different outcomes than glancing encounters that might allow one galaxy to escape after a brief gravitational dance. The dark matter components of both galaxies will merge relatively smoothly due to their purely gravitational interactions, while the gas and dust components experience more complex dynamics involving shockwaves, compression, and heating that can trigger massive bursts of star formation during certain phases of the merger. These starbursts temporarily increase the luminosity of the combined system and help explain why some of the most spectacular galaxies visible in deep space are currently experiencing major mergers that will eventually produce giant elliptical systems. The ultimate fate of Andromeda will be a stable elliptical galaxy roughly 5 times more massive than either original system, containing all the stars from both progenitors arranged in new orbital configurations that reflect the complex gravitational history of their formation through cosmic collision, setting the stage for understanding how the central supermassive black holes from both galaxies will navigate this chaotic environment to find each other and complete their own merger in the heart of our cosmic future. How can something that remains completely invisible to every telescope ever built control the destiny of entire galaxies and determine the precise timing of cosmic collisions billions of years in the future? Dark matter represents perhaps the most humbling discovery in modern astronomy, revealing that roughly 85% of all gravitational mass in the universe consists of an unknown substance that interacts with ordinary matter only through gravity, creating vast scaffolding structures that shape the architecture of cosmic evolution while remaining forever hidden from direct observation. The galactic halos surrounding both the Milky Way and Andromeda extend far beyond their visible boundaries, reaching outward for hundreds of thousands of light years as spherical envelopes of dark matter containing several times more mass than all the stars, gas, and dust combined within each galaxy's luminous disk. These invisible halos act like cosmic anchors that determine how galaxies move through space and respond to gravitational perturbations from neighbouring systems, making them crucial factors in predicting the precise trajectory and timing of the approaching merger between our galactic home and its massive spiral companion. Current computer simulations of the Milky Way-Andromeda collision must incorporate detailed models of both dark matter halos, yet significant uncertainties remain about their exact shapes, masses, and density distributions, leading to variations in predicted collision timelines that can differ by hundreds of millions of years, depending on the specific dark matter properties assumed in each simulation. The challenge of mapping invisible mass requires ingenious indirect techniques that rely on gravitational effects observable through conventional astronomy, including the rotation curves of galactic disks, gravitational lensing of background galaxies, and the dynamics of satellite galaxies orbiting within dark matter potential wells. These observational methods have revealed that dark matter halos possess complex internal structure with dense central regions surrounded by more diffuse outer zones, but the precise details of this architecture remain poorly constrained due to the fundamental difficulty of studying something that produces no electromagnetic radiation across any wavelength of light. The collision dynamics between Andromeda and our galaxy will depend critically on how these invisible halos interact during the merger process. As dark matter particles experience only gravitational forces and therefore behave differently from ordinary matter that can dissipate energy through electromagnetic interactions and shockwave formation. Computer models suggest that the dark matter components of both galaxies will merge relatively smoothly, creating a combined halo system that settles into a gravitational equilibrium over several billion years, while the visible matter experiences more violent dynamics involving gas compression, shock heating, and triggered star formation episodes. The uncertainty in dark matter properties translates directly into uncertainty about collision timing, because the total mass and spatial distribution of each galactic halo determines the strength and range of gravitational attraction between the approaching systems. Recent observations using advanced techniques like weak gravitational lensing have begun to provide more accurate measurements of dark matter halo masses, but these studies still involve significant systematic uncertainties that propagate through theoretical models and affect predictions about our cosmic future. The gentle influence of unseen gravitational fields operates continuously throughout the universe, guiding the formation of large-scale structure through processes that began shortly after the Big Bang and continue today as dark matter halos grow through accretion of smaller substructures and occasional major mergers with comparable systems. Understanding dark matter becomes essential for comprehending not just the Milky Way-Andromeda collision, but also the broader context of cosmic evolution, as these invisible scaffolds provide the framework upon which all visible structures assemble over billions of years of gravitational amplification of tiny primordial density fluctuations. The local group itself represents a gravitationally bound island of matter, dominated by dark matter halos, that will eventually merge into a single massive system, isolated from the general expansion of spacetime by the collective gravitational attraction of its constituent galaxies and their invisible companions. Research into dark matter properties continues to advance through multiple complementary approaches, including underground particle physics experiments searching for direct detection of dark matter candidates, space-based observations of gravitational effects in galaxy clusters, and increasingly sophisticated computer simulations that model the formation and evolution of cosmic structure across the observable universe. The implications of dark matter research extend far beyond academic curiosity, as understanding this mysterious component of reality may ultimately reveal fundamental aspects of physics that remain hidden within our current theoretical frameworks, potentially leading to revolutionary discoveries about the nature of space, time, and the forces that govern cosmic evolution on the largest scales imaginable. What happens when two gravitational titans, each containing the mass of hundreds of millions of suns, begin their inexorable journey through a chaotic stellar battleground toward an ultimate confrontation that will reshape the very fabric of spacetime? Following the initial merger of Andromeda and our Milky Way, both supermassive black holes will find themselves displaced from their original positions at the centers of their respective galaxies, beginning an epic migration through the turbulent environment of the newly combined galactic system that could require over 1 billion years to complete. This cosmic odyssey unfolds through a process astronomers call dynamical friction, a phenomenon that occurs when massive objects move through collections of smaller bodies and gradually lose orbital energy through countless gravitational encounters, similar to how a marble rolling through a sandbox eventually slows down due to friction with individual sand grains. The supermassive black holes act as cosmic vacuum cleaners during this migration, not by directly consuming material but by gravitationally scattering nearby stars into higher energy orbits, effectively transferring their own orbital momentum to the surrounding stellar population through 1 billion individual gravitational slingshot events. Each encounter with a passing star removes a tiny amount of energy from the black hole's orbit while simultaneously accelerating the star to higher velocities, creating a net drag force that causes the massive objects to spiral gradually inward toward the gravitational center of the merged galactic system. The efficiency of this process depends on the density of stars in the galactic core region, with higher stellar densities producing stronger dynamical friction that accelerates the black hole migration, while sparser environments allow the process to proceed more slowly over extended timescales. Computer simulations reveal that the two black holes will likely follow complicated paths through the three-dimensional structure of the merger remnant, sometimes approaching each other closely before being scattered apart by gravitational interactions with dense stellar clusters or massive gas clouds that survived the initial galactic collision. The stellar medium through which these monsters travel consists not only of individual stars, but also globular clusters, molecular clouds, and the debris from disrupted stellar systems that create a complex gravitational landscape capable of dramatically altering black hole trajectories through chance encounters with particularly massive objects. As the black holes sink deeper into the galactic potential well, they begin to influence each other's motion through direct gravitational attraction, creating a binary system with an initially wide orbit that gradually tightens as both objects continue to lose energy through interactions with their stellar environment. The formation of this bound binary represents a crucial milestone in the merger process, because once the black holes become gravitationally linked, their eventual fusion becomes virtually inevitable, barring extremely unlikely disruptions from external gravitational perturbations. The timescale for binary formation and subsequent orbital decay depends critically on the central density profile of the merged galaxy, with steeper density gradients, providing more efficient dynamical friction that accelerates the entire process. While flatter profiles can significantly extend the time required for the black holes to find each other in the vast three-dimensional maze of the galactic core, theoretical studies suggest that the binary hardening process may encounter a temporary stall when the black holes reach separations of roughly 1 parsec, corresponding to the point where most stars capable of extracting orbital energy have already been scattered to larger radii, potentially requiring additional mechanisms such as gas accretion or three-body interactions with stellar mass black holes to drive further orbital decay. However, recent high-resolution simulations indicate that realistic galactic merger remnants contain sufficient stellar density and complex substructure to overcome this potential bottleneck, allowing the black hole binary to continue shrinking through purely gravitational interactions with the surrounding stellar environment. The approaching point of no return occurs when the black holes reach separations of approximately 1 light-year, beyond which gravitational wave emission becomes the dominant mechanism for removing orbital energy, initiating the final phase of their billion-year journey toward ultimate fusion. At this critical distance, the black holes begin to radiate gravitational waves with sufficient power to complete their merger within a few million years, transitioning from a process dominated by stellar dynamics at base to one governed by the fundamental properties of curved spacetime itself, setting the stage for the most spectacular finale in cosmic theatre as two of the most massive objects in our universe prepare to become one. Can you imagine the moment when Einstein's most abstract mathematical prediction becomes the driving force behind the ultimate cosmic collision? As two supermassive black holes begin broadcasting their existence across the universe through ripples in the very fabric of reality? When Andromeda's central monster and our galaxy's own gravitational giant finally approach to within 1 light-year of each other, they cross a threshold that fundamentally changes the nature of their interaction, transitioning from a process dominated by stellar dynamics to one governed by the curvature of spacetime itself, as predicted by general relativity over a century ago. At this critical separation distance, the black holes begin generating gravitational waves with sufficient intensity to drain away their orbital energy at an accelerating rate, initiating what astronomers describe as an inspiraling death dance that will consume the remaining million years of their independent existence. Einstein first proposed the existence of these spacetime ripples in 1916 as a natural consequence of his revolutionary theory describing gravity not as a force, but as the curvature of the four-dimensional manifold that underlies all physical reality, yet he remained skeptical that human technology would ever become sensitive enough to detect such infinitesimally small distortions in the geometry of space and time. The gravitational waves produced by our future black hole binary will carry away orbital energy according to precise mathematical relationships that depend on the masses, spins, and separation distance of the two objects, creating a feedback loop where energy loss causes orbital shrinkage, which increases the orbital frequency, which amplifies the gravitational wave power, which accelerates further energy loss in an exponentially accelerating cascade toward merger. This runaway process transforms the billion-year timescale of stellar dynamical evolution into a comparatively brief final act measured in mere millions of years, during which the black holes spiral inward with ever-increasing velocity, while broadcasting their approach across cosmic distances through undulations in spacetime that propagate outward at light speed. The frequency of these gravitational waves corresponds directly to twice the orbital frequency of the binary system, beginning at extremely low values measured in nanohertz, when the black holes first enter their final approach phase, and gradually increasing through millihertz frequencies detectable by future space-based observatories before reaching the hertz range, accessible to ground-based detectors like LIGO during the ultimate moments of merger. The power radiated in gravitational waves during the final stages of this cosmic dance exceeds the electromagnetic luminosity of all stars in the observable universe combined. Yet this energy manifests as pure space-time curvature rather than photons, making it invisible to conventional telescopes while remaining detectable through extraordinarily sensitive laser interferometry that can measure length changes smaller than 1,000th the width of a proton. LIGO's groundbreaking detections of stellar mass black hole mergers beginning in 2015 have provided crucial validation of Einstein's predictions and revealed the characteristic chirp signals produced when compact objects spiral together under gravitational wave radiation. Though these events involve black holes containing only dozens of solar masses rather than the hundreds of millions contained within supermassive systems, the merger of Andromeda's black hole with our own will produce gravitational wave signals fundamentally different from anything LIGO has observed, operating at much lower frequencies due to the vastly larger masses involved, and requiring specialized space-based detectors capable of measuring gravitational wave oscillations with periods ranging from minutes to hours, rather than the millisecond duration chirps characteristic of stellar mass mergers. Future gravitational wave observatories, such as the proposed LISA mission, will monitor supermassive black hole mergers throughout cosmic history, providing a new window into the formation and evolution of galactic structures that complements traditional electromagnetic astronomy by revealing processes that remain completely invisible to optical, radio, and X-ray telescopes. The inspiraling phase of our future merger will be detectable for millions of years before the final coalescence, allowing future civilizations to track the approaching climax with unprecedented precision and potentially observe relativistic effects such as orbital precession, spin-orbit coupling, and frame dragging, that test general relativity in the strong field regime where gravitational effects become comparable to the speed of light. The mathematical elegance underlying this cosmic choreography reflects deep connections between geometry, physics, and astronomy that Einstein could scarcely have imagined when he first arrived at the field equations describing how matter and energy curve spacetime. Yet the precision of his theoretical framework continues to enable accurate predictions about phenomena occurring on scales and timescales that dwarf human experience while remaining fundamentally governed by the same geometric principles that describe the bending of light around massive objects and the precession of planetary orbits in our solar system. What would it be like to witness the most violent event in the history of our cosmic neighbourhood, when two supermassive black holes containing the mass of hundreds of millions of suns slam together in the final milliseconds of a billion-year journey? The ultimate moment of merger arrives when the two gravitational monsters reach the point where their event horizons touch, and space-time itself becomes so severely distorted that the mathematical descriptions break down, marking the transition from two separate objects to a single, even more massive entity containing over 200 million solar masses concentrated within a region smaller than our solar system. During these final moments, the black holes orbit each other at velocities approaching significant fractions of light speed, creating gravitational wave emissions of such extraordinary intensity that they briefly outshine the combined electromagnetic output of all observable galaxies throughout the universe, though this energy radiates purely as space-time curvature rather than photons visible to conventional telescopes. The merger process unfolds through distinct phases that astronomers describe using evocative terms like inspiral, plunge, and ring down, each characterized by different gravitational wave signatures that encode information about the masses, spins, and internal structure of the colliding objects. The inspiral phase concludes when the black holes reach their innermost stable circular orbit, beyond which no stable orbits exist and the objects inevitably fall toward each other through the plunge phase that lasts only milliseconds despite involving motion across distances comparable to Earth's orbit around the Sun. Computer simulations reveal that the merger itself occurs when the individual event horizons merge into a common apparent horizon, creating a highly distorted space-time region that gradually relaxes into the familiar spherical geometry associated with rotating black holes through the emission of characteristic gravitational wave frequencies during the ring-down phase. The total energy radiated during this cosmic cataclysm equals approximately 3 to 5% of the combined rest mass of both black holes, converting roughly 5 to 10 million solar masses worth of matter into pure gravitational wave energy that propagates outward at light speed as permanent alterations to the metric structure of spacetime. This energy release dwarfs anything previously contemplated in astrophysics, exceeding the luminosity of 100 million simultaneous supernovae, while occurring over timescales measured in mere seconds rather than the weeks or months characteristic of stellar explosions. The newly formed black hole may receive a significant gravitational wave kick if the merger involves black holes with different masses or misaligned spins, potentially imparting recoil velocities of hundreds or even thousands of kilometers per second that could eject the remnant from the galactic center entirely or place it on a highly eccentric orbit within the merged galaxy. These kick velocities arise from the asymmetric emission of gravitational waves during the final moments of merger, creating a rocket-like effect that demonstrates the momentum-carrying capacity of gravitational radiation and represents one of the most dramatic consequences of Einstein's general relativity theory. The magnitude and direction of any recoil kick depends sensitively on the detailed spin orientations and mass ratios of the merging black holes, parameters that remain highly uncertain for the specific case of our future galactic collision, but could profoundly influence the subsequent evolution of the merged galaxy by displacing its central gravitational anchor. Following the immediate merger violence, the newly formed supermassive black hole settles into its final equilibrium configuration through the ring-down process, during which any departure from perfect spherical symmetry radiates away through gravitational waves that decay exponentially over timescales determined by the mass and angular momentum of the remnant object. The resulting black hole will likely possess significant spin inherited from the orbital angular momentum of the original binary system, creating a rotating space-time geometry described by the Kerr metric that exhibits exotic properties such as frame dragging, where the rotation of the black hole literally twists the surrounding spacetime and forces nearby objects to rotate in the same direction. The formation of this spinning giant marks the birth of a new gravitational engine capable of powering future episodes of quasar-like activity if sufficient gas and dust eventually fall within its sphere of influence, potentially transforming the quiet merged galaxy into one of the most luminous objects in the observable universe. The immediate aftermath of merger may witness intense accretion activity as disrupted gas clouds and stellar debris from the collision process spiral inward toward the newly formed black hole, creating temporary episodes of brilliant electromagnetic emission that could briefly outshine entire galaxy clusters before settling into the more sedate long-term evolution characteristic of mature elliptical galaxies, leaving behind only the gravitational wave memories of this extraordinary cosmic event, rippling through space-time toward distant civilizations that may one day detect and decode the signals from our galactic destiny fulfilled. Could a German physicist working alone with nothing but pencil and paper in 1916 have possibly imagined that his abstract mathematical equations would someday enable humanity to detect cosmic collisions occurring billions of light-years across the universe? Albert Einstein's prediction of gravitational waves emerged as an almost inevitable consequence of his revolutionary general theory of relativity, which fundamentally redefined our understanding of gravity by describing it not as a mysterious force acting across empty space but as the curvature of a four-dimensional space-time continuum that responds dynamically to the presence of mass and energy. This radical reconceptualization suggested that space-time itself behaves like a flexible fabric that can be stretched, compressed, and rippled by the motion of massive objects, much like a trampoline surface deforms when weighted objects roll across it or bounce upon its elastic membrane. Einstein's field equations, expressed in the elegant mathematical language of differential geometry, predicted that accelerating masses would generate propagating distortions in this space-time fabric, creating wave-like disturbances that travel outward at light speed, carrying information about the cataclysmic events that produced them. The most powerful sources of these gravitational waves would arise from the most extreme astronomical phenomena imaginable: colliding black holes, merging neutron stars, supernovae explosions, and the primordial fluctuations left over from the Big Bang itself, all creating characteristic signatures that encode the fundamental properties of matter and spacetime under conditions impossible to replicate in terrestrial laboratories. However, Einstein himself remained deeply skeptical about whether these theoretical ripples could ever be detected by human technology, calculating that even the most violent cosmic events would produce space-time distortions so infinitesimally small that measuring them would require detecting length changes smaller than 1/10,000th the diameter of a proton across distances of several kilometers. The challenge seemed so insurmountable that Einstein alternately questioned whether gravitational waves truly existed as physical phenomena or merely represented mathematical artifacts of his coordinate system choices, leading to decades of theoretical confusion and debate within the relativity community about the reality of these elusive space-time oscillations. The experimental quest to detect gravitational waves began in earnest during the 1960s with the pioneering efforts of Joseph Weber, who constructed massive aluminum cylinders designed to vibrate sympathetically when gravitational waves passed through them, though his claimed detections were never confirmed by independent researchers and likely resulted from uncontrolled environmental noise sources. Weber's work inspired a new generation of experimental physicists who developed increasingly sophisticated detection strategies based on laser interferometry, recognizing that gravitational waves would alternately stretch and compress space itself in perpendicular directions, creating measurable changes in the travel times of laser light bouncing between carefully isolated mirrors suspended in ultra-high vacuum chambers. The technological challenges involved in building sufficiently sensitive gravitational wave detectors pushed the boundaries of precision measurement to unprecedented extremes, requiring advances in laser stabilization, vibration isolation, quantum noise reduction, and data analysis techniques that took decades to develop and refine. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, represents the culmination of this multi-generational effort, consisting of two identical 4-kilometer-long interferometers located in Louisiana and Washington state that can detect length changes smaller than 1/10,000th the width of a proton by monitoring the interference patterns created when laser-powered beams travel down perpendicular arms and reflect off precision mirrors suspended as pendulums to isolate them from seismic vibrations. On September 14, 2015, both LIGO detectors simultaneously recorded a distinctive chirp signal lasting just 0.2 of a second, created by gravitational waves from two black holes spiraling together and merging approximately 1.3 billion light-years away, finally vindicating Einstein's century-old prediction and opening an entirely new window for observing the universe through phenomena invisible to electromagnetic radiation. This historic detection, designated GWMFU 914, marked the birth of gravitational wave astronomy and demonstrated that space-time itself can serve as a medium for transmitting information about cosmic events, revealing aspects of extreme physics that remain forever hidden from conventional telescopes operating across the electromagnetic spectrum, while providing the most direct possible confirmation of general relativity's validity under the most extreme conditions nature has to offer. What if you could listen to the universe itself singing, hearing the cosmic symphony of black holes colliding, neutron stars merging and space-time itself ringing, like a bell struck by the most violent events in cosmic history? The extraordinary sensitivity of modern gravitational wave detectors represents perhaps the most ambitious measurement ever attempted by human science, requiring technology capable of detecting changes in distance so minute that they make the diameter of a proton seem gigantic by comparison, achieved through the ingenious application of laser interferometry operating at the very limits of quantum mechanical precision. LIGO's revolutionary design employs kilowatt-class lasers split into two perpendicular beams that travel down 4-kilometer-long evacuated tunnels before reflecting off ultra-pure mirrors suspended as pendulums from elaborate vibration isolation systems, creating interference patterns so delicate that passing gravitational waves can be detected through the tiny phase shifts they induce between the perpendicular laser paths. The mirrors themselves represent marvels of precision engineering, polished to atomic smoothness and suspended by multi-stage isolation systems that filter out seismic vibrations, thermal fluctuations, and even the random motion of air molecules that could otherwise overwhelm the infinitesimal signals from distant cosmic catastrophes. Each detector must distinguish genuine gravitational wave signatures from a cacophony of environmental noise sources, including earthquakes, ocean waves, logging operations, aircraft overflights, and the thermal jiggling of atoms within the detector components themselves, requiring sophisticated data analysis algorithms that can extract coherent astrophysical signals from backgrounds dominated by terrestrial contamination. The global network of gravitational wave observatories has expanded beyond the original twin LIGO facilities to include the Virgo detector in Italy, with its 3-kilometer arms, and the recently operational Kagure facility in Japan, built underground in a mountain to reduce seismic noise and employing cryogenic mirror cooling to minimize thermal disturbances that could mask astronomical signals. This international collaboration enables triangulation of gravitational wave source positions across the sky and provides crucial redundancy that helps distinguish real astrophysical events from instrumental artifacts or local environmental disturbances that might affect individual detectors. The network has now catalogued over 300 confirmed black hole mergers plus several neutron star collision events, revealing a universe far more dynamically violent than previously imagined, and demonstrating that compact object mergers occur throughout cosmic history at rates that challenge theoretical predictions about stellar evolution and binary formation mechanisms. Among the most spectacular recent discoveries, the detection designated GIB 231123 recorded the merger of two black holes with combined mass exceeding 200 times our Sun, representing the most massive gravitational wave event ever observed, and pushing the boundaries of current astrophysical models about how such extreme objects can form through stellar evolution processes. The gravitational waves from our future Milky Way Andromeda black hole merger will produce signals fundamentally different from anything currently detectable by ground-based observatories, operating at much lower frequencies corresponding to the leisurely orbital periods of supermassive objects that require specialized space-based detectors capable of measuring oscillations with periods ranging from minutes to hours, rather than the millisecond chirps characteristic of stellar mass systems. Future space missions like the proposed laser interferometer space antenna We'll deploy 3 spacecraft in solar orbit, forming a triangular configuration with million-kilometer arm lengths, enabling detection of supermassive black hole mergers throughout cosmic history, while remaining immune to terrestrial noise sources that limit the sensitivity of ground-based instruments. These space-based detectors will observe our galactic collision millions of years before the final merger, tracking the inspiraling dance of supermassive black holes as they gradually approach through the emission of increasingly powerful gravitational wave signals that encode precise information about their masses, spins, and orbital dynamics. The sounds these cosmic events would make, if somehow converted to audio frequencies, reveal their underlying physics through characteristic patterns. Stellar mass mergers produce rapid chirps that sweep upward in frequency like birds singing at dawn, while supermassive mergers generate deep, sustained tones that might resemble whale songs, or the lowest notes of a cosmic organ played across timescales measured in geological epochs. This emerging field of gravitational wave astronomy promises to revolutionize our understanding of cosmic evolution by providing direct access to phenomena that remain forever invisible to electromagnetic radiation, revealing the formation history of supermassive black holes, testing general relativity under extreme conditions, and potentially discovering exotic objects or processes that exist only in the most extreme gravitational environments the universe has to offer. What secrets about the fundamental nature of reality can be decoded from the whispers of spacetime itself, as gravitational waves carry encrypted messages across billions of light years from the most extreme environments the universe has ever created? Each gravitational wave detection functions like a cosmic telegram containing a wealth of encoded information about the colliding objects, their individual masses, rotational speeds, orbital dynamics, and the exotic physics governing matter under conditions so extreme that they cannot be replicated anywhere else in the observable universe. The characteristic frequency evolution of these space-time ripples reveals precise details about black hole properties through mathematicals, relationships that connect observable wave patterns to the fundamental parameters governing general relativity, allowing astronomers to measure masses accurate to within a few percent and determine spin rates that encode the entire collision history of each object. The shape of gravitational waveforms carries fingerprints of the merger process itself, revealing whether the colliding objects approached on circular or elliptical orbits, how their spins were oriented relative to the orbital plane, and the degree of mass asymmetry between the two components, all encoded in subtle modulations that sophisticated algorithms can extract from detector noise through techniques borrowed from signal processing and machine learning. These cosmic messengers provide the most stringent tests ever performed of Einstein's general relativity theory, probing spacetime curvature in regimes where gravitational fields approach the theoretical maximum possible. Strengthened matter moves at significant fractions of light speed under conditions that push the mathematical framework to its absolute limits. The precision of these tests has confirmed general relativity's predictions to extraordinary accuracy, while searching for subtle deviations that might reveal new physics beyond the standard model, including modifications to gravity at extreme scales, extra spatial dimensions, or exotic matter, states that could exist only within black hole interiors. Each detection adds another data point to the growing catalogue of cosmic collisions that reveals statistical properties of the black hole population throughout the universe, including mass distributions, formation mechanisms, and evolutionary pathways that connect stellar death processes to the supermassive monsters found at galactic centers. The observed merger rates indicate that compact object collisions occur far more frequently than previously predicted, suggesting that binary stellar evolution follows pathways that efficiently produce gravitational wave sources throughout cosmic history, while revealing gaps in our understanding of stellar physics and galactic chemical evolution. Gravitational waves also probe the fundamental structure of spacetime itself by testing whether gravity truly propagates at light speed, whether gravitational radiation carries energy and momentum as predicted by theory, and whether black holes possess the precise properties demanded by general relativity, rather than representing more exotic alternatives like gravastars or other speculative objects. The polarization patterns of gravitational waves encode information about the symmetries of spacetime and the number of independent directions along which these disturbances can propagate, providing tests of whether gravity operates in the four-dimensional spacetime described by Einstein, or requires additional hidden dimensions proposed by string theory and other unified field theories, advanced data analysis techniques continue to extract increasingly subtle information from gravitational wave signals, including evidence for black hole kicks that occur when asymmetric gravitational radiation imparts recoil momentum to merger remnants, potentially ejecting them from their host galaxies and creating populations of wandering black holes drifting through intergalactic space. The growing sensitivity of detector networks enables observation of increasingly distant events that occurred when the universe was much younger and denser, providing direct windows into cosmic evolution that complement electromagnetic astronomy by revealing processes invisible to photon-based observations across all wavelengths from radio to gamma rays. Future detections will probe the formation of the first generation of black holes in primordial galaxies, the role of dark matter in binary evolution, and the connection between gravitational wave sources and the electromagnetic counterparts that sometimes accompany neutron star mergers through processes like gamma-ray bursts and kilonovae that synthesize heavy elements and distribute them throughout the cosmos. The statistical analysis of hundreds of gravitational wave events is beginning to reveal correlations between black hole properties and their host galaxy characteristics, testing theories about how supermassive black holes co-evolve with stellar populations, and providing insights into the feedback mechanisms that regulate star formation and galactic assembly over billions of years. These cosmic messages from deep space represent humanity's first direct contact with the dynamic universe of curved spacetime, opening entirely new avenues for exploring fundamental physics while demonstrating that the cosmos operates as a vast laboratory for testing theories under conditions far more extreme than any conceivable terrestrial experiment could ever achieve. What would it be like to watch an entirely new cosmic architecture emerge from the gravitational chaos of colliding galaxies as two ancient spiral systems abandon their elegant structure and give birth to something completely different over timescales that span most of the remaining lifetime of the universe? The formation of Milk-Emda represents one of the most dramatic transformations possible in cosmic evolution, involving the complete restructuring of galactic components that have maintained their organized patterns for billions of years, dissolving the graceful spiral arms that define both parent galaxies and redistributing their stellar populations into fundamentally different orbital configurations. This metamorphosis begins during the first close encounter between Andromeda and our Milky Way, when tidal forces generated by mutual gravitational attraction start disrupting the density waves responsible for maintaining spiral structure, gradually unwinding the elegant logarithmic patterns that have guided star formation and chemical enrichment throughout most of galactic history. The spiral arms themselves represent relatively fragile phenomena consisting of compression waves that propagate through galactic disks at speeds different from stellar orbital velocities, creating temporary traffic jams where gas clouds pile up and trigger bursts of star formation that illuminate the characteristic blue-white regions visible in distant spiral galaxies. When major galactic mergers occur, these delicate density waves cannot survive the gravitational turbulence created by tidal interactions, leading to the dissolution of organized structure and the eventual transformation into more spherical configurations where stars move on random elliptical orbits rather than following the circular paths that maintain spiral symmetry. The merger process triggers spectacular episodes of enhanced star formation as shockwaves compress molecular clouds throughout both galaxies, temporarily increasing the birth rate of new stars by factors of 10 or more compared to the sedate stellar nurseries operating in undisturbed spiral systems, creating brilliant starburst regions that can briefly outshine entire normal galaxies. These bursts of stellar activity consume much of the available gas supply within a few 100 million years, exhausting the raw materials needed for continued star formation and leaving behind stellar populations dominated by aging giants that gradually fade from blue to red as the most massive stars exhaust their nuclear fuel and evolve toward their final endpoints as white dwarfs, neutron stars, or black holes. The gravitational stirring associated with galactic collision also heats stellar orbits throughout both systems, increasing random velocities and puffing up the combined structure into a more spherical configuration characteristic of elliptical galaxies, which represent the end products of major merger events throughout cosmic history and dominate the galaxy populations found in dense cluster environments where interactions occur frequently. During this transformation, vast streams of stars get ejected from both galaxies through gravitational slingshot effects, creating extended tidal tails that stretch across millions of light years, and remain visible for billions of years as archaeological evidence of the cosmic collision, while some stellar material escapes entirely to wander through intergalactic space as orphaned populations with no permanent galactic home. The dark matter halos surrounding both galaxies merge relatively smoothly due to their purely gravitational interactions, creating a combined dark matter structure that provides the gravitational scaffold for the new elliptical galaxy, while containing several times more mass than all visible components combined, demonstrating the dominant role of invisible matter in determining the final architecture of merged systems. The central regions of both galaxies experience the most dramatic restructuring as gas clouds collide and compress, triggering massive starbursts that temporarily transform these areas into blazing star formation factories before the available fuel gets depleted and star formation rates decline to levels far below those maintained by spiral galaxies with ongoing gas accretion from intergalactic space. The timescale for complete merger depends on the initial masses, approach velocities and orbital characteristics of the encounter, but computer simulations suggest that Andromeda will achieve dynamical equilibrium roughly 10 billion years after first contact, creating a giant elliptical galaxy containing all stellar mass from both progenitor systems arranged in gravitationally relaxed orbits that reflect the complex merger history encoded in their final spatial distribution. This new cosmic environment will lack the organized gas flows and spiral shock fronts that currently regulate star formation in both parent galaxies, instead relying on occasional minor mergers with smaller satellite systems and the gradual cooling of hot halo gas to maintain minimal levels of stellar birth throughout its extended future evolution as one of the largest galaxies in the local group, representing the ultimate architectural legacy of our cosmic neighborhood's gravitational destiny. Where will our solar system find itself after the cosmic reshuffling of galactic collision, and what are the odds that Earth might someday orbit through the vast emptiness between galaxies rather than within the familiar spiral arms we currently call home? Computer simulations of the Milky Way Andromeda merger reveal that our solar system faces an uncertain gravitational future, with approximately 50% probability of being scattered to a position roughly 3 times farther from the galactic center than our current location in the outer regions of the Orion spiral arm, effectively relocating us to the sparse galactic suburbs where star density drops dramatically and the night sky would appear noticeably different to any inhabitants of distant Earth. This outward migration would occur through gravitational interactions with passing stellar systems and dark matter substructures during the chaotic billion-year period when both galaxies lose their organized structure and settle into the new elliptical configuration of Andromeda, creating a cosmic lottery where stellar systems get randomly redistributed according to the complex dynamics of gravitational scattering events. An even more dramatic possibility involves complete ejection from the merged galaxy, a scenario that statistical studies suggest occurs for approximately 12% of stellar systems during major galactic mergers, sending our entire solar neighborhood on a one-way journey into the nearly empty intergalactic void where the nearest stellar neighbors would be millions of light-years away, rather than the few light-years that currently separate us from Proxima Centauri and other nearby stars. The remarkable aspect of these potential upheavals lies not in their cosmic drama, but in their complete irrelevance to the stability and habitability of our local solar environment, because the vast distances separating individual stars ensure that even the most extreme gravitational scattering events would have essentially no direct impact on planetary orbits, Earth's climate, or any other aspects of life as we know it within the protective gravitational embrace of our Sun. The safety of our solar system derives from fundamental scaling relationships in astronomy. While galactic distances are measured in thousands of light-years and stellar separations span multiple light-years, our planetary system occupies a tiny region less than 1 light-day across, making it effectively immune to the gravitational chaos occurring on galactic scales during merger events. To appreciate this isolation, consider that if our Sun were reduced to the size of a period on this page, the nearest star would be located roughly 10 miles away, while Earth would orbit at a distance smaller than the width of a human hair, illustrating why stellar encounters remain virtually impossible even during the most violent phases of galactic collision. The long-term survival of our solar architecture depends primarily on the Sun's nuclear evolution rather than galactic dynamics, as our star will continue burning hydrogen for approximately another 5 billion years before entering its red giant phase and eventually becoming a white dwarf, timescales that dwarf the duration of the galactic merger events and render questions about orbital stability around the galactic center largely academic for Earth's future habitability. Our potential new position in the cosmic landscape could actually prove advantageous in some respects, as relocation to the galactic outskirts would reduce exposure to supernova, gamma-ray bursts and other high-energy phenomena that occur more frequently in the dense stellar environments near galactic centers, while providing clearer views of external galaxies and cosmic structures currently obscured by dust and stellar populations within our current galactic neighborhood. The concept of complete ejection from Andromeda might seem catastrophic, but such wandering solar systems would retain all their internal structure and dynamics, while gaining the unique perspective of intergalactic space, where the absence of nearby stars would create utterly pristine dark skies unmarred by light pollution from stellar neighbors, offering hypothetical future astronomers unprecedented views of distant galaxy clusters and large-scale cosmic structure. The longevity of our local stellar environment extends far beyond any conceivable galactic reorganization, as gravitational binding within our immediate solar neighborhood proves remarkably robust against external perturbations, with the Sun's gravitational influence extending outward to the Oort cloud at distances measured in light years where cometary orbits remain stable over billions of years, despite occasional passages through galactic spiral arms and encounters with molecular clouds. Statistical analysis of stellar trajectories during galaxy mergers indicates that most stellar systems preserve their local kinematic relationships, meaning that familiar constellations might persist for millions of years, even after dramatic changes in our galactic coordinates, though the gradual proper motion of individual stars would eventually alter these patterns regardless of merger dynamics. The ultimate lesson from these cosmic relocations emphasizes the hierarchical nature of gravitational organization in the universe, where tightly bound systems like our solar family remain essentially unaffected by dramatic rearrangements occurring on larger scales, demonstrating that astronomical stability operates across multiple levels of cosmic architecture, from planetary systems to galactic superclusters. What would happen if the dormant gravitational monster created by merging supermassive black holes suddenly awakened with an appetite for cosmic destruction, blazing forth with luminosity that could outshine entire galaxy clusters and fundamentally alter the environment of every star system within thousands of light years? The merger of Andromeda's central black hole with our own galactic giant creates conditions ripe for triggering the most spectacular feeding frenzy in cosmic history, as the collision process inevitably funnels vast quantities of gas, dust, and stellar debris toward the newly formed supermassive object through gravitational torques that overcome the angular momentum barrier, preventing material from spiraling inward. This cosmic banquet begins when shockwaves from the galactic collision compress molecular clouds throughout both systems, driving turbulent gas flows that gradually lose their orbital energy through viscous dissipation and magnetic field interactions, creating a sustained supply of fuel capable of powering quasar-level activity for millions of years after the initial merger event. The formation of an accretion disk around the merged black hole represents one of nature's most efficient energy conversion mechanisms, capable of transforming up to 42% of infalling matter into pure radiant energy through the process of gravitational potential release as material spirals inward toward the event horizon at velocities approaching significant fractions of light speed. This accretion process heats the surrounding gas to temperatures exceeding 100 million degrees Celsius, creating a blazing plasma environment that radiates intense electromagnetic emissions across the entire spectrum from radio waves to gamma rays, with peak luminosities that can rival 100 million simultaneous supernovae, concentrated into a region smaller than our solar system. The active galactic nucleus created by this feeding activity would transform Milconda into one of the most conspicuous objects in the observable universe, visible as a brilliant quasar from distances exceeding billions of light years, while simultaneously sterilizing much of the surrounding galactic environment through intense radiation fields and high-velocity particle winds that strip away planetary atmospheres and inhibit star formation across vast regions. The duration of these active phases depends critically on the available fuel supply and the complex feedback mechanisms that regulate accretion rates, with theoretical models suggesting that major quasar episodes could persist for anywhere from 1 million to 100 million years before exhausting easily accessible gas reservoirs or triggering self-regulating processes that reduce the inflow rate. The variability of quasar activity follows patterns observed in distant active galaxies where brightness fluctuations occur across timescales ranging from hours to centuries as the accretion disk responds to instabilities, magnetic field reconnection events, and the occasional disruption of wandering stars that venture too close to the central engine and get torn apart by tidal forces before contributing their mass to the feeding process. The effects on the surrounding galactic environment would be profound and long-lasting, as powerful jets of relativistic plasma launched from the vicinity of the spinning black hole could extend across millions of light-years, carving enormous cavities in the intergalactic medium while depositing sufficient energy to prevent galaxy clusters from cooling and forming new stars for billions of years. These jets arise from the interaction between magnetic fields threading the accretion disk and the rotation of the central black hole, which acts like a cosmic dynamo capable of launching collimated beams of high-energy particles at velocities exceeding 99% of light speed through processes that remain among the most energetic phenomena known in astrophysics. The radiation pressure from intense electromagnetic emissions near the black hole creates powerful winds that can expel gas from the central regions of the galaxy at velocities of thousands of kilometers per second, effectively regulating the star formation rate throughout the merge system and potentially explaining the observed correlations between supermassive black hole masses and the properties of their host galaxy bulges. The eventual return to quiescence occurs when the readily available gas supply becomes depleted through either consumption by the black hole or expulsion by radiation-driven winds, leaving behind a massive but dormant gravitational engine that subsists on the occasional disruption of passing stars or the slow accretion of hot gas from the surrounding galactic halo. This cycle of activity and dormancy likely repeats multiple times throughout the lifetime of the merged galaxy, triggered by minor mergers with smaller systems or the gradual inflow of cooled gas from the intergalactic medium, creating episodic bursts of quasar activity separated by extended, quiet periods that could last for billions of years. The legacy of these active phases persists long after the central engine returns to dormancy, visible in the form of radio-emitting lobes, shock-heated gas cavities, and chemically enriched regions where heavy elements synthesized during previous episodes of intense star formation continue to influence the evolution of stellar populations throughout the cosmic future of our merged galactic home. How do astronomers study invisible objects that emit virtually no light yet contain the mass of hundreds of millions of suns, using detective techniques so sophisticated they can discern the whispers of gravitational giants across distances that dwarf human comprehension? The challenge of observing supermassive black holes represents one of the most ingenious applications of indirect astronomical methods, requiring scientists to infer the presence and properties of these cosmic monsters through their subtle gravitational effects on surrounding matter, and occasional brief episodes of electromagnetic activity that provide fleeting glimpses into otherwise hidden realms. NASA's Chandra X-ray Observatory has maintained an extraordinary vigil over Andromeda's central regions for more than 2 decades, accumulating nearly 900,000 seconds of observation time across approximately 100 separate pointings that have revealed the faint X-ray signature of M31's dormant supermassive black hole during its extended period of gravitational hibernation. These prolonged observations have documented what astronomers poetically describe as the murmur of a sleeping giant, detecting baseline Sirach-Ray emissions at luminosity levels roughly 10 billion times fainter than the theoretical maximum possible for an object of this mass, demonstrating just how efficiently supermassive black holes can remain virtually invisible despite their enormous gravitational influence. The sparse X-ray photons collected by Chandra's sensitive mirrors originate from the hot plasma environment surrounding the event horizon, where occasional gas clouds or stellar debris venture close enough to be heated to millions of degrees before either being consumed by the black hole or expelled through magnetic field interactions that remain poorly understood despite decades of theoretical investigation. The interpretation of X-ray flares observed in 2006 and 2013 requires careful analysis of spectral properties, timing variations, and spatial distribution patterns that can distinguish genuine black hole activity from other potential sources such as X-ray binaries, supernova remnants, or background contamination from unrelated astronomical objects within the same field of view. These outbursts provide crucial insights into the feeding mechanisms operating around dormant supermassive black holes, suggesting that even quiescent systems occasionally experience episodes of enhanced accretion when disrupted stellar material or molecular clouds breach the inner regions where gravitational tidal forces become strong enough to overcome magnetic pressure and angular momentum barriers. Radio observations using interferometric arrays such as the Very Large Array and the Event Horizon Telescope Network have attempted to map magnetic field structures in the immediate vicinity of M31's central black hole, though the extreme distance and low activity level make such measurements extraordinarily challenging compared to similar studies of our own galactic centre, or more active supermassive black holes in nearby galaxies. The radio emissions that do reach Earth from Andromeda's core region likely originate from synchrotron radiation produced by relativistic electrons spiralling along magnetic field lines, providing indirect evidence for the complex magneto-hydrodynamic processes that govern plasma behaviour in the strong gravitational fields near massive black holes. The fundamental challenge of studying dormant black holes lies in their remarkable efficiency at remaining invisible across the electromagnetic spectrum, producing emission levels so low that they often fall below the detection thresholds of even the most sensitive astronomical instruments, forcing researchers to rely on statistical analysis of long-term monitoring campaigns and careful subtraction of contaminating background sources. The most reliable method for measuring supermassive black hole masses involves tracking the orbital motion of individual stars in the galactic nucleus, using adaptive optics systems and sophisticated spectrographic techniques to detect tiny Doppler shifts caused by stellar velocities that can exceed 10,000 kilometers per second in the innermost regions where gravitational acceleration approaches relativistic values. These stellar dynamics measurements require years or decades of patient observation to map complete orbital periods, demanding unprecedented precision in astrometric positioning and radial velocity determination that pushes ground-based telescope technology to its absolute limits, while providing the most direct possible evidence for compact massive objects at galactic centers. Advanced data analysis techniques borrowed from particle physics and signal processing enable astronomers to extract meaningful astrophysical information from datasets contaminated by instrumental noise, atmospheric turbulence, and foreground stellar populations that can overwhelm the subtle signatures of black hole activity. The growing sophistication of observational methods continues to reveal new aspects of supermassive black hole behaviour, including evidence for intermediate mass companions, episodic jet activity, and complex interactions between central engines and surrounding nuclear star clusters that help regulate the long-term evolution of galactic bulges throughout cosmic history, while demonstrating the remarkable ingenuity required to study objects that by definition cannot be observed directly. How can scientists peer billions of years into the future with mathematical precision using supercomputers as cosmic time machines that simulate the gravitational ballet of entire galaxies across epochs that dwarf all of human history? The challenge of predicting galactic collision outcomes requires sophisticated numerical techniques that model the motion of millions of individual particles representing stars, dark matter, and gas clouds as they respond to constantly changing gravitational fields over timescales spanning most of the remaining lifetime of the universe. N-body simulations represent the computational equivalent of building-scale models of the cosmos, where each particle acts as a test mass subject to gravitational forces from every other particle in the system, creating a mathematical framework that can accurately reproduce the complex dynamics governing galactic evolution through purely Newtonian mechanics applied on astronomical scales. The HGPU's code, utilized by researchers studying the Milky Way Andromeda encounter, harnesses the parallel processing power of graphics processing units originally designed for video games, converting thousands of specialized cores into a computational engine capable of tracking gravitational interactions between up to several million particles simultaneously, while maintaining sufficient numerical accuracy to resolve stellar orbital periods and collision cross-sections. These calculations require months of continuous processing time on some of the world's most powerful supercomputing facilities, generating terabytes of data that encode the complete three-dimensional evolution of both galaxies from their current separated state through first encounter, multiple close passages, and eventual merger into a stable elliptical configuration. The computational complexity scales approximately as the square of the particle number, meaning that doubling the resolution requires 4 times more computing resources, creating practical limits that force researchers to balance numerical accuracy against available processing power, while developing clever techniques to represent collective gravitational effects without explicitly tracking every individual star. Testing different initial conditions reveals the sensitive dependence of collision outcomes on poorly constrained parameters, such as the precise approach velocity, impact parameter, orientation of galactic rotation planes, and the detailed mass distribution within each dark matter halo, leading to variations in predicted merger timelines that span roughly 2 billion years, depending on the specific assumptions incorporated into each simulation. The uncertainty in collision timing reflects fundamental observational challenges in measuring proper motion across the vast distances separating our galaxy from Andromeda, where even the most precise astrometric measurements struggle to detect the tiny angular displacements that would reveal the transverse component of galactic motion relative to the radial velocity determined through Doppler shift observations. Current estimates suggest first close approach could occur anywhere between 3 and 5 billion years from now, with the range of possibilities determined primarily by uncertainties in Andromeda's tangential velocity component that affects whether the encounter will be head-on, glancing, or involve multiple orbital passes before final coalescence. The role of intergalactic medium density adds another layer of complexity to collision predictions, as the tenuous plasma filling the space between galaxies creates drag forces that gradually dissipate orbital energy and alter approach trajectories through mechanisms analogous to atmospheric friction, but operating over cosmic distances and timescales. This intergalactic gas consists primarily of hydrogen and helium at temperatures around 1 million degrees Celsius, maintained in ionized form by ultraviolet radiation from quasars and other energetic sources throughout the universe, creating a barely detectable but dynamically significant component that influences the long-term evolution of galaxy groups and clusters. Simulations must incorporate realistic models of this background medium while accounting for its uncertain density distribution, temperature structure, and magnetic field properties that remain poorly constrained by current observational capabilities, adding systematic uncertainties to collision predictions that may not be resolved until space-based observatories provide more sensitive measurements of diffuse X-ray emission from hot intergalactic plasma. Refining these computational predictions requires continuous improvement in both observational inputs and numerical techniques, including better measurements of galactic masses, dark matter halo profiles, internal velocity dispersions, and gas content that serve as initial conditions for simulation codes, while advances in computational algorithms enable higher resolution models that can resolve smaller scale processes affecting merger outcomes. The feedback loop between observation and theory drives steady progress toward more accurate predictions, as each new measurement helps constrain simulation parameters, while computational experiments suggest which observational quantities would most effectively reduce remaining uncertainties about our cosmic future. Future improvements in computational power and algorithmic sophistication promise ever more detailed simulations that will eventually resolve individual stellar encounters, gas cloud dynamics, and magnetic field evolution throughout the merger process, transforming these mathematical time machines into comprehensive laboratories for exploring galactic evolution under the most extreme conditions imaginable. What revolutionary discoveries await us as humanity prepares to deploy the most sophisticated astronomical instruments ever conceived, capable of peering deeper into space and time than any previous generation could imagine? The next decade promises an unprecedented expansion of our observational capabilities through a constellation of advanced space telescopes and ground-based facilities that will transform our understanding of supermassive black holes, dark matter, and galactic evolution, with precision measurements extending far beyond current technological limits. The James Webb Space Telescope represents just the beginning of this observational revolution, offering infrared sensitivity capable of detecting individual stars within Andromeda's nuclear regions, while providing spectroscopic analysis of gas flows and stellar populations that could reveal evidence for past black hole activity episodes buried within the galaxy's complex formation history. Webb's extraordinary infrared vision will pierce through cosmic dust clouds that currently obscure our view of galactic cores, potentially discovering hidden, supermassive black holes in nearby galaxies while mapping the distribution of heavy elements that encode the chemical signatures of ancient stellar generations influenced by previous episodes of quasar activity and galactic feedback processes. Future X-ray observatories currently under development will surpass even Chandra's remarkable sensitivity, employing larger collecting areas and improved detector technologies that could monitor M31's dormant black hole continuously for decades, while detecting much fainter activity levels that might reveal the subtle feeding processes maintaining these gravitational giants during their extended periods of apparent quiescence. The proposed Athena mission and other advanced X-ray telescopes will combine unprecedented sensitivity with high-resolution spectroscopy capabilities, enabling detailed analysis of hot plasma motions near supermassive black holes while mapping temperature and density structures that encode information about magnetic field configurations and accretion disk physics operating under the most extreme gravitational conditions known to exist. Revolutionary gravitational wave detectors scheduled for construction over the next 2 decades will dwarf current facilities in both size and sensitivity, with the Einstein telescope proposing underground interferometers featuring 10-kilometer arm lengths cooled to cryogenic temperatures, while the Cosmic Explorer concept envisions 40-kilometer facilities capable of detecting supermassive black hole mergers throughout most of the observable universe with exquisite precision. These next-generation gravitational wave observatories will monitor the approach of Andromeda's supermassive black hole toward our own galactic center for millions of years before the final merger, providing unprecedented tests of general relativity, while revealing details about black hole spins, orbital precession effects, and exotic phenomena such as scalar field emissions that could signal physics beyond the standard model. Space-based gravitational wave. Missions like the proposed LISA constellation will operate in the frequency range perfectly suited for detecting supermassive black hole in spirals, using laser interferometry between spacecraft separated by millions of kilometers to achieve sensitivity levels that could track binary evolution from initial pairing through final coalescence with temporal resolution measured in minutes rather than the current limitations of ground-based detectors. Advances in dark matter detection techniques promise to revolutionize our understanding of the invisible scaffolding that dominates galactic collision dynamics, combining direct detection experiments deep underground with increasingly sophisticated weak lensing surveys that map dark matter distribution around galaxy clusters and along cosmic web filaments where galactic encounters occur most frequently. Next-generation optical telescopes such as the Extremely Large Telescope and 30-meter telescope will achieve angular resolution sufficient to track individual stellar orbits around M31's central black hole, providing direct measurements of gravitational effects that could reveal deviations from general relativity or evidence for exotic alternatives to conventional supermassive black hole models. The synergy between electromagnetic and gravitational wave astronomy will create unprecedented opportunities for multi-messenger observations of cosmic events, potentially allowing simultaneous detection of black hole mergers through both gravitational radiation and electromagnetic counterparts such as optical transients, gamma-ray bursts, or neutrino emissions that encode complementary information about extreme physics processes. Continuous monitoring programs extending over multiple decades will be essential for detecting rare events, such as tidal disruption episodes when individual stars venture too close to supermassive black holes, providing laboratories for studying matter behavior under conditions that cannot be replicated through any conceivable terrestrial experiment. The importance of sustained observation campaigns cannot be overstated, as many key discoveries in black hole astronomy have emerged from patient monitoring that revealed unexpected variability patterns or rare events that occur only occasionally over timescales measured in years or decades, emphasizing the need for long-term commitments to astronomical surveillance that transcend typical funding cycles and institutional boundaries while maintaining the technological infrastructure necessary to capitalize on future breakthrough opportunities. How can the human mind truly comprehend temporal scales so vast that the entire history of our species represents less than a fleeting moment compared to the cosmic patience required for galaxies to complete their gravitational dance across the void? The 4.5 billion years separating us from the Milky Way Andromeda collision encompasses a duration roughly equal to the entire age of our planet Earth, stretching from its formation through accretion of cosmic debris around the young sun to the present moment when complex life has evolved sufficient intelligence to contemplate its own cosmic future with mathematical precision. To place this extraordinary timescale in perspective, consider that if Earth's complete geological history were compressed into a single calendar year, the collision with Andromeda would occur sometime during the following January, while all of recorded human civilization would occupy only the final few minutes before midnight on December the 31st, emphasizing just how brief our current technological epoch appears when measured against the stately rhythms governing galactic evolution. The evolution of life on Earth provides perhaps the most meaningful context for understanding these cosmic timescales, as 4.5 billion years ago our planet had only recently cooled enough to support liquid water oceans, while the first primitive microorganisms were just beginning to emerge from the primordial chemical soup that would eventually give rise to the spectacular diversity of complex organisms we observe today. During the equivalent time period stretching into our cosmic future, evolution will have countless opportunities to explore new biological pathways, potentially producing forms of intelligence and consciousness so advanced that they would regard our current scientific understanding as we might view the cognitive abilities of single-celled bacteria swimming in ancient seas. The Sun itself operates according to temporal rhythms that provide reassuring stability across these vast scales, as our stellar engine has already burned through roughly half of its hydrogen fuel supply during the 4.5 billion years since the solar system formed, leaving approximately 5 billion years of steady energy output before it exhausts its core hydrogen and begins the transformation into a red giant star that will eventually engulf the inner planets. This stellar timeline means that the Andromeda collision will occur while our Sun remains in its current stable main sequence phase, ensuring that any inhabitants of Earth during that distant epoch will still enjoy the same reliable solar heating that has sustained terrestrial life throughout its entire evolutionary history, though the specific forms that life might take after billions of additional years of development remain utterly beyond our current imagination. Human civilization represents an almost incomprehensibly brief chapter in this cosmic story, having emerged from our pre-agricultural ancestors only about 12,000 years ago, and developed modern science within just the past few centuries, timescales so short that they vanish entirely when compared to galactic collision dynamics, or even the formation timescales of individual stars within stellar nurseries scattered throughout both approaching galaxies. The patience required by astronomical processes reflects fundamental physical constraints on how rapidly massive systems can redistribute their energy and angular momentum through gravitational interactions, creating natural timescales that depend on system size, mass distribution, and the strength of relevant physical forces rather than arbitrary human preferences for rapid results or immediate gratification. Finding peace in these vast temporal scales requires a profound shift in perspective that recognizes the universe operates according to its own intrinsic rhythms, neither hurried by human urgency nor delayed by our impatience, but following the inexorable mathematical relationships that govern everything from planetary orbits to stellar evolution to the expansion of spacetime itself across cosmic distances. The contemplation of deep time can produce either existential anxiety about human insignificance or profound wonder at our extraordinary privilege in existing during an epoch when intelligent life has emerged capable of understanding its place within these vast cosmic cycles, representing what may be an extremely rare occurrence in the history of the universe, given the precise conditions required for complex chemistry and biological evolution. These cosmic timescales also provide perspective on the temporary nature of current human concerns and conflicts, suggesting that many issues dominating contemporary discourse will be forgotten long before even the earliest stages of galactic approach become apparent to future astronomers, while the fundamental questions about consciousness, meaning, and purpose that have occupied philosophers throughout history will likely persist as long as intelligent beings continue to exist anywhere in the universe. The gentle rhythm of cosmic evolution offers a form of temporal meditation that can reduce anxiety about immediate uncertainties while fostering appreciation for our participation in processes vastly larger and more enduring than individual lifespans, reminding us that we are temporary arrangements of matter and energy briefly capable of contemplating our own existence within the magnificent tapestry of cosmic time that stretches from the Big Bang to whatever ultimate fate awaits our expanding universe. What deeper truths about the fundamental nature of reality might be revealed when two supermassive black holes finally merge in the most extreme gravitational laboratory the universe has ever created, pushing the boundaries of physics far beyond anything achievable through human experimentation? The collision between Andromeda's central monster and our own galactic giant will provide unprecedented opportunities to test Einstein's general relativity under conditions where space-time curvature approaches theoretical maximum values and matter accelerates to velocities that challenge our understanding of causality, energy conservation, and the relationship between geometry and physics that underlies all modern cosmology. These cosmic laboratories operate under physical regimes so extreme that they can probe aspects of gravitational theory inaccessible through any other means, including the behavior of spacetime near singularities, the emission properties of gravitational radiation in strong field environments, and the potential existence of exotic phenomena such as naked singularities, extra spatial dimensions, or modifications to general relativity that become apparent only when gravitational fields reach strengths billions of times greater than anything experienced in terrestrial physics. The connection between galactic evolution and supermassive black hole growth represents one of the most profound mysteries in modern astrophysics, suggesting that these invisible gravitational engines somehow regulate star formation, chemical enrichment, and structural development throughout their host systems through feedback mechanisms that operate across spatial scales, ranging from individual stellar neighborhoods to entire galaxy clusters containing thousands of member galaxies. Understanding this co-evolutionary relationship requires comprehending how black hole accretion processes generate outflows capable of heating intergalactic gas to temperatures that prevent cooling and subsequent star formation, effectively controlling the rate at which cosmic structures assemble over billions of years, while simultaneously determining the final masses achieved by both central engines and their surrounding stellar populations. The merger of supermassive black holes also provides unique insights into the early universe, when similar events occurred much more frequently during the epoch of rapid galaxy assembly, roughly 10 billion years ago, creating a population of gravitational wave sources that future space-based detectors will observe as a cosmic background signal encoding information about structure formation, dark matter properties, and the equation of state governing cosmic expansion during crucial phases of universal evolution. These ancient merger events helped establish the tight correlations observed between black hole masses and galactic bulge properties throughout the local universe, suggesting that fundamental physical processes link the largest and smallest scales of cosmic organization through mechanisms that remain poorly understood despite decades of theoretical investigation and increasingly sophisticated observational campaigns. The ongoing mystery of dark matter becomes particularly acute when contemplating galactic collisions, as these invisible components dominate the gravitational dynamics determining collision timelines, merger outcomes, and the subsequent evolution of combined systems, yet remain completely undetectable through electromagnetic radiation, while revealing their presence only through gravitational effects that challenge our basic understanding of matter, energy, and the composition of physical reality. Current theories propose that dark matter consists of exotic particles produced during the first moments after the Big Bang, interacting with ordinary matter only through gravity while forming the cosmic scaffolding upon which all visible structures assembled through gravitational amplification of primordial density fluctuations. Yet alternative possibilities include modifications to gravitational theory itself or entirely new physics operating on galactic scales. The even more mysterious phenomenon of dark energy adds another layer of complexity to cosmic evolution, driving the accelerating expansion of space-time itself through unknown mechanisms that appear to operate in opposition to gravitational attraction, while determining the ultimate fate of the universe and the maximum size achievable by gravitationally bound structures like galaxy groups and clusters. Our evolving picture of cosmic destiny incorporates these discoveries into increasingly sophisticated models of universal evolution that extend from the quantum fluctuations responsible for seeding cosmic structure formation through the present epoch of galaxy assembly to distant futures when star formation ceases and black holes become the dominant objects in a cold, dilute universe, expanding toward maximum entropy. The merger of Andromeda with our Milky Way represents just one episode in this vast cosmic drama, yet provides crucial insights into processes that have shaped the universe throughout its history, while offering glimpses of fundamental physics that may hold keys to understanding consciousness, information theory, and the relationship between mathematical abstractions and physical reality that enables intelligent beings to comprehend their place within cosmic evolution through scientific investigation and theoretical modeling that reveals hidden connections between seemingly disparate phenomena operating across astronomical scales of space and time. What gift do we receive from contemplating cosmic events so distant in time that they transform our understanding of permanence, change, and our extraordinary privilege to exist during an epoch when intelligence has emerged capable of predicting its own galactic future with mathematical elegance? The beauty of long-term astronomical prediction lies not merely in its technical sophistication, but in its demonstration that the universe operates according to comprehensible principles, allowing finite minds to grasp infinite processes through patient observation, careful reasoning, and the accumulated wisdom of countless generations who have gazed upward and wondered about humanity's place within the cosmic story unfolding around us. Our journey tonight through the gravitational choreography awaiting our galactic neighbourhood reveals both the remarkable certainty possible in some aspects of cosmic forecasting, and the fundamental uncertainties that remind us how much mystery still surrounds even our most confident scientific predictions about supermassive black holes, dark matter, and the ultimate fate of cosmic structures evolving over timescales that dwarf geological epochs, the precision with which we can predict orbital mechanics across billions of years while remaining uncertain about dark matter properties, black hole formation mechanisms, and the detailed physics governing galactic merger outcomes, reflects the hierarchical nature of scientific understanding, where some phenomena yield readily to mathematical analysis, while others continue to challenge our theoretical frameworks and observational capabilities. Yet this blend of knowledge and ignorance enhances rather than diminishes the wonder of living in a universe we can partially understand, creating endless opportunities for discovery and learning that ensure future generations will continue finding new aspects of cosmic evolution to explore, measure, and comprehend through increasingly sophisticated instruments and theoretical insights. The comfort found in cosmic cycles and transformation emerges from recognizing that change represents the fundamental nature of existence at every scale, from subatomic particles to galactic superclusters, with the approaching merger between Andromeda and our Milky Way representing just one example of the continuous recycling and reorganization that has characterized universal evolution since the Big Bang and will continue long after our current stellar configurations have been forgotten by cosmic time. This perspective offers solace for those concerned about impermanence in human affairs, suggesting that transformation rather than stasis defines the natural order, with even the most massive and seemingly permanent cosmic structures participating in ongoing cycles of assembly, evolution, and eventual dissolution that maintain the universe in a state of perpetual creativity and renewal. The invitation to continued learning and observation extends beyond professional astronomy to encompass anyone who finds meaning in understanding our cosmic context, whether through following future discoveries about gravitational waves, contemplating the night sky with a renewed appreciation for its invisible complexities, or simply carrying forward the sense of wonder that emerges from realizing how extraordinary it is that matter has organized itself into forms capable of contemplating their own existence within vast scales of space and time. Each new astronomical discovery adds another piece to the cosmic puzzle, while simultaneously revealing how much more remains to be understood, ensuring that the process of scientific exploration will continue providing insights into fundamental questions about consciousness, purpose, and the relationship between intelligence and the physical universe that gave rise to beings capable of asking such questions in the first place. The approaching collision between our galaxy and Andromeda reminds us that we live during a brief but remarkable moment in cosmic history when intelligent life has emerged and developed sufficient understanding to predict its own astronomical destiny, while remaining humble about the vastness of what lies beyond current knowledge and technological capabilities. As you settle into sleep tonight, perhaps you can find peace in knowing that the same gravitational forces gently holding your body to Earth's surface also orchestrate the grand dance of galaxies across cosmic time, connecting your immediate physical experience to processes operating on scales that encompass the entire observable universe, while demonstrating the fundamental unity underlying all natural phenomena, from quantum mechanics to cosmological evolution. The soft rhythm of your breathing participates in atomic and molecular cycles that connect you directly to stellar nucleosynthesis processes occurring billions of years ago in the cores of massive stars that enriched the interstellar medium with heavy elements essential for biological chemistry, linking your existence to cosmic history while suggesting that consciousness itself may represent one of the universe's most remarkable achievements in organizing matter and energy into forms capable of understanding and appreciating their own cosmic heritage. Rest well tonight, cosmic citizen, knowing that you are part of an ongoing story vast enough to encompass galactic collisions, yet intimate enough to include the gentle wonder you experience while contemplating your place within this magnificent cosmic tapestry that continues weaving itself across dimensions of space and time that stretch from the quantum realm to galactic superclusters and beyond.